Hello everyone, thank you for coming to my presentations. Today I'm going to present a momentum to gradient direction algorithm with variable step size applied to solve practical output constraint issue for active noise control. Active noise control is used to attenuate noise in the environment by generating an anti-noise with the same amplitude but opposite phase of the primary noise. In the ANC system, it needs a secondary speaker to play the control signals to generate the anti-noise. This brings a problem that once the amplitude of the control signal generated by ANC algorithm exceeds the limitation of the speaker, it will bring output saturations of the speakers and further brings the divergence of ANC algorithm. Previous research has proposed a two-gradient algorithm to overcome output saturations of the ANC algorithm. These methods update the coefficient in the same direction as a conventional FX-LMS algorithms. Once the output signal power exceeds the constraints of the speaker, the algorithm will change the update direction to reduce output powers. However, this method brings the oscillation effect caused by the constant changing directions, as the figure shows here, and also the small step size caused by slow convergence, which will limit the practical implementations of this algorithm. Here we propose a momentum to gradient method with a variable step size strategy. In this method, the update directions are divided into two cases, depends on whether the output signals exceeds the constraints. The two directions are set as the opposite directions according to the two-gradient method and solve the output saturations, where the momentum factors are added in the first update directions to increase the convergence speed of the ANC algorithm. And what's more, the step size used in two update equations is also different and determined by a variable step size strategy. In order to eliminate the oscillation caused by the inappropriate step size selection with alternatives updating the control filters, a variable step size selection is introduced, where the first step size is determined by the minimum values of these two values, which is calculated by the common ratio multiplied the step size in the previous time and the minimum values we determined in the system when the output signal powers exceeds the constraints. And the second step size is determined by the Lagrange factors multiply the first step size at the same time. The stability analysis shows the step size bounds in different situations. When the output power of the secondary source within the constraints, the step size bounds is related to the momentum factors and the maximal values of the eigenvalues, where in the second cases, the output power of the secondary source exceeds the constraints. The step size bounds is determined by the Lagrange factors and the maximal eigenvalues. Also, the time constant depends on the momentum factors. After analysis, we can see if the momentum factor is larger than 0 but smaller than 1, the step size bounds and the convergence speeds were both improved. The simulations are conducted to validate the noise reduction performance of the 2GD momentum algorithms with variable step size strategy. Here we apply clipping functions to simulate the output constraints of the speakers. 4 algorithms are tested in the simulations: the FX elements, rescaling 2GD and 2GD momentums. From the result, we can see that with the output constraints, the rescaling and the 2GD momentums have cancelled the saturation effects, whereas the FX elements caused serious saturation effects in the simulation. The second simulation used to validate the noise reduction performance in a static environment. The optimal value without the output constraints is calculated and shown in the figures as the star notions, and the suboptimal value is calculated with the output constraints as shown in the figures as different notations. And the red line in the figures shows the weight boundaries with the output constraints. So here we can see that with the output constraints, the rescaling and 2GD momentums, as well as the 2GD has reached the suboptimal values, where the FX-LMS algorithms breaks the boundaries of the weight and then reach to the optimal values. Also, we can see that without the variable step size strategies, the 2GD and rescaling algorithms has reached the suboptimal values but brings oscillating effects around the suboptimal weights. The figures of the weight changes also shows that the rescaling algorithms and the 2GD algorithms has brings the oscillating effect for the culture filter's weights. In the third simulations, we tested the noise reduction performance in a varying environment. Here, in the first simulations, the suboptimal culture filters is calculated at 0.89 and 0.66, and with the change of the primary path and second path in the NC system, the suboptimal culture filters is changed to 1.63 and 1.17. As shown in figures, the boundary of the weight also changes from the red line to the blue lines, and it is similar to the previous simulations. The rescaling algorithms and 2GD algorithms has brings several oscillating effects around the suboptimal culture filters, while the FX-LMS has break the weight boundaries and reach to the optimal values without the output constraints. From the weight changes figures, we can see that the 2GD momentum algorithms has achieved a higher convergence speeds compared with the FX-LMS and the 2GD algorithms with the help of the momentum factor. The conclusions can be made for these presentations are listed in these pages. Thank you for your attention. If you have any questions or want to discuss further, please come to my poster sections.